Welcome live to the Quantum Summer Symposium 2022, where we want to give you an update what the Google Quantum AI team and our collaborators have been up to over the last 12 months in terms of building quantum hardware and quantum software, and also tell you a little bit how you can interact with our team. So I structure my introduction by answering questions that our team is asked often. So starting with, hey, how far along are we towards building a quantum computer of commercial relevance? If you attended the Quantum Summer Symposium before, you will have seen this roadmap, which we published in 2020, a little bit with the idea to organize our community and industry around the goal of building a useful large quantum computer. And this roadmap to get to this goal is broken down in a number of milestones. The first milestone we achieved in 2019, when we showed that a quantum computer can do a task much, much faster than a classical computer. And the next milestones to get to the commercially valuable machine are about achieving quantum error correction as a technology. That is a rite of passage our community will have to go through. We will need error correction to have enough operations on each qubit to run complex algorithms. So you may have seen this already on the archive a few days ago, but I'm honored or privileged to tell you that due to the skilled and hard work of the entirety of our team, we have achieved our next milestone, which is demonstrating experimentally in practice that the theory of quantum error correction works, and we built a logical qubit prototype. So we called this shot also 2 years ago, where we said our milestone 2 implements surface code error correction in the well-known way that you take the logical information you want to store in a qubit, but you don't store it just in a single physical qubit, but you introduce redundancy. So you have an ensemble of qubits, and then as you make this ensemble larger, for example, you go from a 3 by 3 to a 5 by 5 array, then what you should observe is that the logical error probability comes down. So as the logical qubit sits there, you have the error rate reduced by a suppression factor we call lambda. Let's go maybe a little bit more into the details. This was a plan, and now here you see the actual experimental data. And here on the left, you see the experimental setup. So we did a code distance 5 compared to code distance 3 experiment. So we have 5 by 5 data qubits, which store the logical qubit information. And we have d square minus 1, so that's 5 by 5 is 25. That makes it 24 measure qubits that essentially peak in, and they, in a roundabout way, so that it can not learn about the logical information we want to store, because that would collapse it. But these measurements can still learn about errors that occur over time. And then within this array of 5 by 5 data qubits, we can tuck in a number of 3 by 3 arrays, which are organized in an analogous way. And then we can compare the error rates as the logical qubits are sitting there over various algorithmic time cycles. And we also have logical Z and X operators to measure the state of the qubit. And then you see that here on the right, it looks like we wanted it to look, namely that the logical error probability goes down as we go from code distance 3 to code distance 5. So essentially what this experiment shows for the first time experimentally, that we pass the break-even point. So even though we have more qubits, more gates, more stuff, so more errors can happen, the error density due to the quality of our hardware is low enough that the decoders don't get overwhelmed and they can make sense of the information they see and give us more reliable logic information. So to go a little bit more into detail how one instance of this experiment works, you start out by taking your data qubits and then you put them into an eigenstate of, let's say, the Z bases, the local Z operators, and you do this for all your data qubits. So essentially, you initialize your logical qubit in eigenstate of the logical Z operator. And then we measure our error syndrome operators, and that essentially puts our overall system into a well-defined superposition state that stores the information of one logical qubit. And now if nothing would go wrong, everything goes well, we essentially keep checking in through our measure qubits. Did anything go wrong? Did anything go wrong? And if nothing happens, these measurements would always read the same. But if something happens, let's say, for example, a cosmic ray drops in and flips a data qubit, or flips a measure qubit, or something goes wrong with a gate operation, or something goes wrong while measuring, then error syndromes would occur. Essentially, the measure qubits would change their state, and this changing of state is a detection event. And then a decoder comes in, it knows it's in our initial state, and it watches the history of all these measurements. And then it can tell us what logical Z, we can do the same analogously for X, what logical Z observable or measurement we should see. And then in the last round of the experiment, we actually measure all our data qubits, and then we can see experimentally what was the Z value. And if it coincides, we are happy, no error, everything went well, the decoding worked out correctly. But if it's different, then we do have an error and it counts against our error rate. And then if we look at this one more time, just the same data, just plotted a little bit differently, not directly in terms of error rate, but in terms of fidelity. And here you see again, we achieved for the first time passing the break-even point. So essentially by scaling up a logical surface code qubit from code distance 3 to 5, we see that the fidelity for the larger code distance is larger than the fidelity for the smaller grid. And that constitutes achieving our milestone 2. So one thing that is very important for our team, we want to be sort of a trusted advisor to the community. And one thing we are very cautious or conscious about is to not overhype results. And I don't want to overhype our milestone 2 result either, because it's not the end of the road yet. There are 4 more milestones to go. And in particular, the next milestone will be a hard one. It is achieving one long-lived logical qubit with a low error rate, let's say of 10 to the minus 6 or 10 to the minus 9 would be better, so that we can do many operations per qubit and run the famous complex quantum algorithms. And what will it take? We can ask the question, what will it take to reach milestone 3? So in parallel to doing the experiments that I just described, we also did additional experiments to give us a little bit of a map. Where do we need to improve our system to scale to milestone 3? And here the right figure shows this nicely. It shows you on the x-axis is the code distance. So the experiment with the surface code, which protects against phase flip and bit flip errors simultaneously. A qubit is a 2-dimensional object, so 2 error channels can be there. And here we see the 2 code distance 3 and 5 results, and you see it comes down by a little bit as we want to. But we could also run a simpler code, which is only 1-dimensional repetition code. Here you can only protect against one of the two errors, and you can choose, for example, to protect against phase flip errors. But the reward for having the simpler code is we can already extrapolate or go to much larger code distances and see what happens. And what happens is exactly what you want to see. As you go higher in code distance, step by step, each time the logical error rate is reduced by a factor, in this case about a factor of 3 each time. And at the very bottom, you get you run into a noise floor caused by cosmic rays. But what we want to see now in the future is essentially reproduce this line of dots for the surface code. And we will, as we make larger chips, we'll get more dots for the surface code line, and then hopefully these line of dots come even lower than the one we see for the repetition code. Yeah. What we also did, we did careful modeling of the hardware and the experimental results we saw. For example, we modeled how do the different error channels contribute to the overall error rate. And there you can see, for example, CZ error is still a big chunk, or what is marked as DD stands for dynamic decoupling. It's really the idling errors that happen while a qubit is waiting for being measured and reset. So these are large chunks that we need to reduce. And that leads us to a to-do list, what we still need to do to reach a logical qubit with a low error rate. So in essence, we need to improve, as always in life, quantity and quality. For example, we need to get to a lambda larger than 4 as a minimum. Why is this? Now, if your lambda is too small, then you need too many physical qubits to express one logical qubit. So it gets a very large array. Large array means many detection events can happen. So your error graph is very large, and your decoder has to do a lot of work. And because decoding is expensive, they can't keep up anymore with the quantum information progressing. Yeah, so to achieve this larger lambda, we need to increase our coherence times, and equally good is reducing the idling time. So you do more within a given coherence time. So reducing the time it takes to do reset and measurement, that's an important goal. Our modeling also showed how detrimental crosstalk and leakage is. Most error correcting codes assume decorrelated errors. Of course, in real life, this is never the case. And I already touched on the fact that cosmic rays can be very deleterious. They cause large correlated error events, bad for error correction. So these are things we will need to work on. So now on the scale side, if you just assume, let's just try to stay where we are in terms of our lambda, but just make the chips larger, what would this take? And I break this down here by the different technologies involved. So chip fabrication, we feel in principle we could stamp out a 1,000 qubit chip today in our new QFab 1 facility here across the street. Cryostats, actually one reason we published our roadmap is to recreate a little bit the virtuous cycle of the semiconductor industry and alert other adjacent industries to business opportunities. So large enough cryostats are now commercially available from multiple vendors. The control electronics that we have today is largely suitable for our 1,000 qubit experiment, which we expect for milestone 3. But after that, you will want to go to a CMOS technology, but it's not yet needed for the next milestone. And then maybe the area that causes still or needs most work is 3D integration. I often like to say that our chips are a little bit like hairballs because we have like one wire per qubit, so there's a lot of wires. Accordingly, packaging and wiring technologies need to be developed that can support large arrays of qubits. Yeah, so this is what we still need to do for our next milestone. So going to the next question that, of course, many in our community, I'm sure you have heard it, is what will be the first commercially valuable applications? So let me tell you a little bit what's top of mind there in different areas. It's not exhaustive. So first of all, surface code error correction is expensive. It creates overhead. So therefore, we published this paper that shows that we need at least quartic scaling to overcome this overhead. And unfortunately, there is still a scarcity of algorithms operating on classical data that provide that good of a scaling advantage. But that's not to say that there is not nice progress in this area. I just feel the community would pay more attention and we would have more people designing novel quantum algorithms. But among the work that is happening, let me call out, because it's on our team, the work by Edward Fay and a group of quantum AI engineers and collaborators. They had this nice result showing that QAOA, the quantum approximate optimization algorithm, outperforms all known classical algorithms for an optimization task, in that it can guarantee a better quality solution for this task. So this is in the segment of computer science where algorithms come with guarantees and proofs. Then another area where progress is nicely soldiering on is reaching a quantum advantage in chemistry. So a nice example work there is with our collaborator Boehringer Ingelheim, with which we costed out what does it take to model the enzyme P450 to a level of accuracy that is interesting for pharmacology. So we look at these algorithms, cost them out, try to see how big the computational volume has to be, and invent algorithmic tricks to bring this cost down. And then there are two more areas that I find rather exciting. One, results around quantum machine learning at the intersection of quantum sensing and quantum computing. And I have a separate slide on that. And then maybe the most heartwarming thing to me was watching this Cambrian explosion of NISQ circuits that happened over the last 12, 24 months, where we essentially make good on Richard Feynman's dream, and we study the physics of exotic states of matter where quantum phenomena play a role. So let me tell you a little bit more about those last two results. Actually, the first one, which generates this insight that transducing quantum data to quantum memory enables a learner to learn with exponentially reduced sample complexity. Means it needs exponentially fewer examples to learn a task. And this was work done in collaboration with Caltech. So Robert Wang and Caltech, and then Jared McLean on our side, they spearheaded this work. And essentially, I think it's a bit of a sea change in science, because so far all scientific observation, and when Galileo was standing there looking through his telescope, looking at the night sky, and he would do a little sketch of what he saw, he took a classical piece of data. And all science and all machine learning works with classical data. But what if you were to replace this by a probe that can be coherently, that hosts a quantum state that is coherently evolved under the inflowing flux of photons? In that case, you can prove that a quantum learner that would have access to this state, to this quantum buffer, as we like to call it, and if you now have a quantum machine learning algorithm processing this data, then you can learn certain properties of the observed system with, again, exponentially reduced need for training data. That's pretty exciting for a machine learning person like myself. The other area I mentioned, the Cambrian explosion of quantum simulation. And not to brag, but yeah, to brag a little bit, there's a high impact paper almost every month, from time crystals all the way down. Our last experiment was on bound states of photons. So essentially what we found is that there are little clumps of bound together photons. And that's a pretty amazing physics insight, that under the driver of a suitable unitary, such states can emerge. because you don't have to be much of a physicist to know that photons typically do not like to interact. Who hasn't sat at a campfire with two flashlights and then watches how the flashlights go straight through each other without interacting? So now, of course, if I put my business hat on, then there's, of course, a little bit of a concern here. How long will it take from an interesting novel physics insight to an actual technical artifact that would help a person on Main Street? You could also say, hey, all the work you have done so far, you could in principle have done on a classical device still. Yes, this is true, but having a noisy programmable quantum device caused or motivated the invention of new algorithmic tricks that otherwise would have never come about. So we arguably have, or not arguably, we do have novel physics insights that were triggered and motivated by people trying to program the chips. And here's a little bit a map of which areas maybe come ripe for simulation going forward. So I want to conclude a little bit by answering the question, how can I take advantage of Google's quantum computing service? And in this year, we worked in what we call the chaperone mode. So a collaborator at a university or at a company would come to us, say, hey, I'm interested in running the following experiment or algorithm. And then after some pre-vetting, we select some of these experiments and then help our partners, collaborator, execute them. So a lot of the papers you saw before were with collaborators done in this way. But we are working hard to broaden the access to the Google quantum computing service. And one piece we did is we launched CERC 1.0. So this is the first truly stable release of CERC. And it's important for our users because now you have the certainty that your investment is still valuable in the future, and that we have proper versioning. So the future, your code will be compatible with future versions of CERC. We also launched, you may have seen this announcement just yesterday or early this morning, that we launched a quantum virtual machine. I love this name because essentially it says what it is. So on a classical processor, we have a faithful simulation, a mirror image of one of our processors that are sitting here in the lab, and they have very realistic noise models. So you can use a quantum virtual machine to pre-try your algorithms and see how they would behave on an actual noisy hardware processor. And then we can, if the results are good, take it eventually to processors that are too large to be modeled on classical machines. And of course, we can offer quantum virtual machine at Google scale. So there are no queues, so thousands of users can use those simultaneously. So to wrap up, another question I often hear is, hey, the work sounds amazing, this seems very futuristic, and we would love to be part of the team. How can I become part of the team? So there the answer is, our team is rapidly growing. So this is actually a woefully old picture, but I like the energy in this picture. But it's a pre-pandemic picture. By now we're at least 3, maybe 4 times larger than this. And our team is growing at the maximal responsible speed. I feel you can grow a team. So with 40-50% growth year over year. So obviously we are hiring, and we have on the 3rd day of the Quantum Summer Symposium a nice virtual career fair. Our researchers put a lot of work in, so please attend it and see how you can engage with our team. And one message we always like to transmit is many technologies are needed to make a large quantum computer happen. We are also strong believers that we need to bring together different approaches, for example, to designing a qubit. So if you have a degree or experience with other types of qubits other than superconducting qubits, still please reach out to us. There are many who come from adjacent fields. So with this, I want to thank you all for attending, and I hope you will have fun listening to the talks that will go into more detail about the things that I told you about in my introduction.